So let me start with let me look that up. So this is the first topic in today's discussion. The focus is about general properties. I already motivated the problem last time. So the question is the following. We will base entirely on this 6 commutation relations relating the x, y, z components of a 3-dimensional vector that we will call some angular momentum, whatever the realization may be. The x, y, z component at the magnitude square. We have seen, I think you did last term, that the commutation relation of the x and y, z components are cyclic, meaning Lx, Ly goes like Lz with an IH bar and so on with a cyclic relationship. And then the magnitude square is commuting with any component. By these commutators and the idea about commutation relation, we already know it is legal. It is possible to look for simultaneous eigenstate of the magnitude square and any one component. Usually we will pick that component to be called the Z component, but it is actually our choice. It doesn't matter. But by the relationship, because the components themselves do not commute, if you know one, you can't know precisely the other two. Therefore, it is legal to look for L square and Lz simultaneous eigenstate. Our question will be, what can be said about the eigenstate and eigenvalue of this L square and Lz that solely based on these 6 relations? We don't need to write them into alpha, theta, phi, real space coordinates, etc. Okay, so that is the question. That is what we meant by general. So I hope that at least you know what we are asking. To make it very clear that we are not working on orbital angular momentum here, but a general idea about angular momentum, we will replace L's by the general symbol J. So from now on, we will use Jx, Jy, Jz, and J square. When we consider orbital angular momentum, we can take it as a special case of what we are going to discuss and call it L. And then when we discuss spin angular momentum, we could take it as another special case and call J S, okay? Because they're so important, they have their own symbols. In general, we will just call the angular momentum J. And later on, we will use the same symbol J for the total angular momentum, but that is later. I understand not all students like the taste of a 10-page mathematical derivation, okay? Sometimes I even don't like it. Therefore, in the next 2 pages or so, I outline to all students here the key steps and the key conclusions, so that when we go into the derivation a bit later, first, you have a map in your mind where we are getting to, okay? That is important. Secondly, you can make connection better. You know what is the flow of logic. Third, for those who even don't like to see the proof, fine. The results are more important than the proof, because no matter you know how to prove it or you don't know how to prove it, the results are true. And it is more important to understand the content of the end product and move on with that set of results and understand more physics. Okay, so that is my philosophy. Therefore, at the beginning, before we do any proof, I would like to sketch to you the big picture of the proof. There are a few key steps. We will start off with a possible eigenstate of jz j squared. That's reasonable. We know that we can find simultaneous eigenstate. And this possible eigenstate for jz has an eigenvalue called beta. That is the z component. And then for the magnitude square, the eigenvalue is called alpha. That means square root alpha will be the magnitude of j. Okay? The first and most important idea is that for any vector quantity, any component we set here cannot be longer than the magnitude of the vector. Okay? So therefore, when we say this, it's just by physical sense. Any component cannot be longer than the magnitude. Okay? So that is the criteria that will set very stringent requirement on the form of the eigenvalue beta and alpha. Okay, this is for z, jz, this is for j squared. Okay, it turns out that this very simple requirement will give us very important results regarding the form, the mathematical form of beta and alpha. Next step, just like what you did in harmonic oscillator. Okay, I read your notes. I know that you did that. We will define two auxiliary operators. One is called J plus. That is defined through Jx and Jy. You will see the definition later. All right. So we will have a J plus operator, the function of which is, if we start with this proposed eigenstate with beta eigenvalue for z, this raising operator J plus will keep on adding h bar to the z component state. That is to say, it will take one jz eigenstate with beta eigenvalue to a higher one with beta plus h bar and do it again to another one with plus 2h bar and do it again plus 3h bar and so on. So pictorially, it says, if I start here with an eigenvalue z of jz that is beta, operate j plus on it, the result is to take the eigenstate to higher and higher, see my cross, and higher and higher and higher and higher and keep on going. Jz eigenstates. Okay. Now in the same picture, I intentionally marked off this is how long the j square, the magnitude of j, that vector is. Okay. Immediately you see a problem, right? If I keep on operating jz, it may go off bound longer than the magnitude of the vector. So there is something wrong and becomes unphysical if it does so. Therefore, there is a criteria here emerges that we must stop this, keep this increasing by h bar somewhere, and it should stop before it go across the limit. Okay, so that is the big picture number 2. Big picture number 3 is similar. We will define a lowering operator J minus, the action of which is to take the JZ eigenstate with eigenvalue decreasing by h bar, and then another h bar, and other h bar, and so on. Pictorial, it means if I start from the same proposed state beta here, J minus will be doing the following. It takes the eigenstate to yet another eigenstate with beta minus h bar eigenvalue, and then lower by h bar and lower by h bar, and so on. It could go off bound. This is the length of the vector. If it does go off bound, something is unphysical. Therefore, we must stop it. Okay? So there is another criteria here emerge. Therefore, J plus, we want to stop it somewhere, and that value we call beta maximum. That is as long the Z component can be. J minus, we have to stop it somewhere and call it beta minimum. That is the last value before it go off bound. Okay? Next, based on this very simple criteria, we can prove that these two values stop at the highest Z component and the lowest Z component, they are related. How? They are related by a minus sign. That is to say, if that is beta maximum, the Z component on the negative side will be minus beta maximum. With this, we can also ask for that criteria, what is the form of the magnitude square alpha? It turns out that it must take on this form. If you find the maximum, then this is the eigenvalue of the magnitude square. Now, it started to look familiar, right? L times L plus 1 h bar square, okay? So that is what we are going to prove. And now the game becomes the following. We know that there is a cutoff beta maximum, and we know that there is a lower cutoff beta minimum, and we know that if we start from somewhere called 4h bar, for example here, that must stop at minus 4h bar because they are off by a minus sign. And previously, we defined the action of the raising and lowering operators. These operators will take the JZ eigenstate to another one, but always in step of h bar. Either 1 h bar up or 1 h bar down. So that is to say, the highest one and the lowest one, you must be able to do this. From here, h bar down, h bar down, h bar down, see my cross, and it will reach the minimum, okay? So it means from here to there, it must be some multiple, integer multiple of h bar, okay? So that is the criteria. And one way to realize that is this example. I start off with an integer h bar, and then in step of h bar, I will reach minus that same number. But this is not the only possibility. we could as well start with a half integer h bar for the highest value, and then instead of h bar, so this is an example of 2.5 h bar, instead of h bar, we can also reach minus beta maximum, okay? So for this general criteria, there are two possibilities and only two possibilities. The maximum Z component of any angular momentum can only take on two types of numbers, integer or half integer, okay? Think about it. If I start somewhere very strangely, okay, 2.8 h bar, then J minus will take me to 1.8, 0.8, minus 0.2, minus 1.2, minus 2.2, and then minus 3.2. It will never end, and then the criteria of the component being shorter than the magnitude will be violated. Therefore, 1.8 h bar and its all other step values are not allowed by this commutation relations. Okay, so let me summarize. At the end, we will see the following three statements. The magnitude square of any angular momentum must take on this form. Okay, and then for the quantum number J here regarding the magnitude square, this can only take on two types of values, integer or half integer, not any other thing. Then for a given J quantum number for the length of the angular momentum, the Z component will start with JH bar and then go downward in steps of H bar and reach the minimum one being minus JH bar. Together, there will be 2J plus 1 Z components, okay? And that, if you don't like any mathematical proof, just remember this box, and then you can move on happily to the next section, but that will be 15 pages later, okay? So that is the big picture. Is that okay? So that will be the outline, the proof that we are going to do, okay? Now, I hope that you already see through what we are going to get. The results are very common, right? You know that. You have seen it in orbital angular momentum, but orbital angular momentum takes on the option of integer, J being integer, okay? L equal 1 is P state, L equals 2 is TD state. We have also seen spin last time, and spin takes on the other possibility. The S is half and half only for electron, and that is half integer. Here, we are saying that relying on the commutator alone, these are the possible results, okay? So that is what we want to do. Now, let me go through the details of the proof. For those who don't like proofs, okay, relax and take your breakfast. Now, let's start. We are looking for J square and JZ simultaneous eigenstate. That is as best as we can do, allowed by the commutation relations. Therefore, let us define an eigenstate. The symbol is phi, okay? We don't know what it is, we don't care what it is. We will focus on the eigenstate. So on the eigenvalue. So the J square, we introduce it is the eigenvalue, all right? Recall, actually the square root of alpha is the length of the vector J, okay? That is the magnitude of the vector. And since this is simultaneous eigenstate, so the same phi, we propose it to have an eigenvalue beta. So we start off with general alpha and beta, and we start to look for what are the constraints or the regulations that beta and alpha must obey, okay? But we know one very simple criteria. Z component cannot be longer than the vector itself, okay? So this is represented by this inequality. Here, I use a square because it is Z component square shorter than the magnitude square. If you take a square root, that will be square root alpha bigger than or equal to beta, okay? The same thing. Next, we start defining J plus and J minus. This is very similar to your harmonic oscillator. And this week, one of the sample questions is about this raising and lowering operators in harmonic oscillator as well, as a reminder of what they are. And the TA will work out some rather harsh integrals of harmonic oscillator states on both sides, different states, and with an operator x cubed, x4 power in between. That will prepare you for problem set 2, where you will exercise some perturbation theory techniques. Okay, so if you kind of forgot about how A plus A dagger A work, try the sample question this week, okay? Go to exercise class. Let's get back to business. J plus J minus, the definition is very simple. We have Jx, Jy around, right? So J plus is defined as Jx plus I, Jy, and J minus is minus I, Jy. That's the only difference. As a remark, these are physical things, X component, Y component, so they are Hermitian. Thereby, if you do a plus I something combination, this is not Hermitian. This is not Hermitian as well. But don't worry, I haven't claimed that they are physical quantities. They are just auxiliary, help us do the proof, okay? Now we start seeing a whole page of formulas. That's why I give you the big picture first. You know what we are getting at. With J plus J minus, it's natural to ask, do they commute? If not, what is the commutator? It turns out that J plus J minus commutator is 2h bar Jz. Recall we have Jx, Jy embedded in these two operators. This is the key, the first key result. The proof goes here. So J plus J minus, by definition, is the product. Okay, and then you multiply them up, you will see Jx, Jx, that is a Jx square. You see Ijy minus Ijy, that will be a Jy square with a plus in between. So we have that, okay? Then you will have some Jx, Jy cross term. It's easy to see that you will have a Jx, Jy, and then a Jy, Jx. And in quantum mechanics, you cannot easily flip them randomly. keep the order, thereby you pick up a commutator. But we are playing with the commutation definitions only and no more information, all right? Thereby, we can make use of that. Jxjy is IH bar JZ, okay? So that's simple. So I summarize this line here for J plus J minus product. This is a line that we will use later. Similarly, you can work out the opposite order, J minus J plus, and you will find a similar thing, but only with a minus sign here. Same thing. Then the commutation relation is this minus this, and thereby the first two terms cancels, and you have this 2H bar JZ. Done, okay? A remark. If we add a JZ square here and subtract it out here, you see a J square combination, J square plus JY square and JZ square, okay? And that will also be useful later. Good. Next, rather naturally, we are going to ask, what will J plus do to the eigenstate phi, which is an eigenstate of JZ? In doing so, it's natural to ask first, what is the commutation between JZ and J plus? Easy. By definition, it is X plus IY. Therefore, we hit on two commutators, Z and X component here, and then Z and the Y component with an I here. Notice that again, we are restricting ourselves with limited information, only operators, not anything more. But fine, we are done. This commutator by definition is his. The other one is this, okay? And therefore, we have that, okay? And now, we see an interesting situation. The commutation is related to J plus again, okay? So we have this very important result. JZ J plus commutator equals H bar J plus, all right? You can work out the other one, JZ J minus, that is minus H bar J minus, okay? So a little bit boring, but mathematics, every step is true. Now, the physics kicks in. What do J plus do to the eigenstate phi? Okay, so now to answer this question, we take this phi that has eigenvalue beta for JZ. We first operate J plus on it and ask whether it is still an eigenstate of JZ, okay? So the left-hand side has some physical thought behind it. Take phi, which is an eigenstate of JZ, operate J plus on it and ask, is it still an eigenstate of JZ? If it does, there will be a number times J plus phi, okay? So that is the idea. Now, we know this commutation, okay? Here, we have a term JZ J plus. Therefore, it is H bar J plus J plus JZ. There are two terms here. I move the second term to the right-hand side, okay? So I have this term here. And then JZ operate on phi will give me beta phi by definition. We propose it to be so. And beta is a number, thereby it goes through. So the first term will give us beta h plus phi. So that is the same beta h plus phi, all right? Now the second term, h plus phi, and I have an extra h bar. So this is the first, the eigenvalue. Okay, what does it mean? It means the following. J plus operating on an eigenvalue of Jz will increase the eigenvalue by h bar. Take it once h bar step up in eigenvalue. Okay? In other words, J plus phi is indeed an other eigenstate of Jz. Okay? And the eigenvalue is beta plus h bar. Okay? Similarly, we can answer what J minus does. It will take a state of eigenvalue beta of Jz to 1 h bar lower. Okay? So summary, J plus J minus do something as summarized in this box. It will take eigenstate of Jz in h bar steps higher into other eigenstates or h bar lower into other Jz eigenstates. And this is why we have these names, raising and lowering operators for J plus and J minus. So now we are in the big picture step 2. Then we also wonder, what J plus J minus will do to the magnitude square of that state? Will it change it to an other length? Okay, so this is the question. We start off with this proposal. The magnitude square is alpha for this eigenstate phi. Now, we want to ask, after we operate J plus phi on it, what is the length square? All right. So we have to look for some previous answer that we have derived. Remember, we can try this thing out, okay? So we have J square, J plus, and therefore we have J square, Jx plus Jy, okay? And since J square commute with any components, they are commute, okay? So J square commute with J plus J minus, that's the conclusion. Let's work it out. If I operate J plus on phi and ask what is, whether it's still an eigenstate and what is the eigenvalue, I can flip the order because they commute. And since this is an eigenstate of eigenvalue alpha, there's a real number that can come out, and the conclusion is J plus phi is an eigenstate, but the length of the vector will remain the same. Alpha will stay the same, okay? Similarly for J minus, okay? So conclusion, another summary, this box. J plus J minus will create different eigenstate for Jz, but it will not change the length of the state. So alpha will stay the same, okay? And now, we are at this stage. We saw J plus taking JZ up, and then it shouldn't get out of bound. That is the next argument, okay? We have also seen J minus decrease the eigenvalue of JZ by H bar in steps, and it shouldn't go out of bound. So we must stop it. We have also seen that no matter what J plus J minus do, this magnitude of the vector is not changed. Okay, so that is what we have now. So let me go back to the formulas. So the physics now is it increase or decrease in step of H bar, all right, but the component cannot be longer than the magnitude. That's the point, okay? So as it goes up in H bar steps, there should be a maximum that is shorter than the length. When the state H plus take the state up to there, it cannot go further up. All right, so that is the physics, the physical picture. Reaches beta maximum, but then cannot go up anymore. We have a cutoff, okay? So that maximum value, we will call it beta maximum. Similarly, there will be a minimum value that J minus take it down and should stop here. It cannot go one more step lower. We will call it beta minimum, okay? At this point, we don't know how they are related. We will find it out. And accompanying this beta maximum eigenvalue of JZ, we call that particular state phi beta maximum. This is an eigenstate of JZ that carries the maximum Z component. Similarly, this is the eigenstate that carry the minimum Z component eigenvalue. How could we stop the action of J plus? Remember, we worked out what J plus does. Okay, so this is how J plus operate on JZ eigenstates. Start here one eigenstate, take it to the next higher one, okay? And this new eigenstate will have an eigenvalue H bar higher, okay? So in order to stop the raising of the Z component, the argument is as follows. Sooner or later, phi will reach phi beta maximum. At that point, this state already has beta maximum eigenvalue for the Z component. Now, we don't want it to go outbound. So the only way to stop it is that when this particular maximum Z component eigenstate appears to be here, so you want to take it one step further. So J plus operate on J maximum, okay? The way you can stop it is that when it hits here, it is 0. Okay? So when this is 0, nothing will follow. Okay? So that is the way to define, or you have a formula actually to look for phi this eigenstate. Okay? So because you have Jx plus Ijy, so you have an equation so that you can solve for the highest Z component eigenstate. But that is the idea behind which we can stop it, cut it off. Okay? So when it reaches the highest eigenstate, don't go anything higher. And it is still true because this equation becomes 0 equals 0. We haven't violated this equation. Similarly, as it reaches the lowest one, when you still operate J minus on it, it better be 0. So that is the other way to cut off the lower one. Okay, so now we have found a way to stop it. Next, the question is whether this beta maximum is in some way related to this beta minimum. Okay. A few pages ago, when we work out the commutation of this, J plus J minus, we arrive at these two lines. Take the difference, we will get the commutator 2h bar JZ. Now, we make use of these two lines again, but in a different form. I hinted at before. If I add a JZ squared term here, the three terms will give me J squared. But I have to subtract that out again. So I have this and copy this thing through. Okay, so I hope that you see why this is so. And in a similar way, the second line, do the same thing, just off by a sign. Okay, so let me summarize. J plus J minus is this chunk. J minus J plus is this chunk. Okay, we will use it. So we have cut it off at the highest Z component by enforcing this to be 0. So now we play with J minus J plus this higher state. And we know the answer is 0. Because this is defined to be 0. Okay? But on the other hand, we have J minus J plus being these three terms. Okay? And it operates on the highest Z component eigenstate. And now something interesting come out. We have shown this remains eigenstate of J square of the same eigenvalue alpha. So the first term gives us an eigenvalue. We have shown that this, okay, is the last, the highest eigenvalue of JZ that take on beta maximum. So JZ square will give us beta maximum square. Okay. The last term again, JZ, this one will give me beta maximum, the same state. So we have from here to there. Nonetheless, when we start off, it is 0. And suddenly we have a relationship between the length square actually, the length square of the angular momentum and the maximum value being beta maximum times beta maximum plus h bar. Some familiar formulas start to emerge. Similarly, we can work at the lowest end. J minus operate on the eigenstate, the most negative component should be 0. By definition, cut it off. Now we operate J plus on it. J plus operate on 0 is 0. Okay? But this combination is this. Following similar arguments, we have the magnitude square is also given by beta minimum times beta minimum minus h bar. Okay? So now we have a relationship. We are talking about the same length for the angular momentum. So that alpha in 16, equation 16, should be the same alpha in equation 17. Thereby, this ought to be equal that. Okay? That is a crucial moment of the proof. And therefore, we get this relationship between the lower cutoff, the most negative Z component, and the most positive Z component, because the component cannot be longer than the length of the vector, and the commutation relations has enforced a relationship. The longest Z component is the same as the longest negative component in magnitude. So beta maximum, beta minimum, they're off by a sign. Okay, so this is a crucial relationship. So now, just to make sure that you haven't got lost, you have seen this. For example, in D state in atoms, you have L equals 2, thereby you have plus 2H bar being the LZ largest one to minus 2H bar being the most negative Z component, okay? But here, we are not entirely talking about orbital angular momentum, but general, okay? So let's get back to business. So we have seen that J minimum, beta minimum is minus beta maximum. And we also seen that by operating from the higher state with J minus, it should come down instead of H bar. H bar, H bar, H bar to negative and arrive at beta minimum. Thereby, beta maximum minus beta minimum must be an integer times H bar. So we have this line. Okay, that makes use of our argument about the action of J plus and J minus. And now, since this is minus, no, this alone is minus beta maximum, this becomes 2 beta maximum, and we have the criteria. The Z component longest one is n over 2 H bar. That are the only options. What does it mean? It means the Z component, the longest one, can be either an integer H bar or a half integer H bar. No other things. Okay? And at the end, now let me put all the things together. We have seen that alpha is given by that. Okay? And understanding that beta maximum, beta minimum must be off by H bar in steps. Now this must take on either integer or half integer. Okay? We call this a quantum number J. Okay? That can be 3. Then you have 3, 2, 1, 0, minus 1, minus 2, minus 3 as the Z components. H bar, of course, okay? Or J could be half integer, meaning 2.5. Then you have 2.5, 1.5, 0.5, minus 0.5, minus 1.5, minus 2.5. Okay? And therefore, we can write it in a more general form. If we introduce a quantum number J, which is n over 2, depending on whether n is even number, then J is integer. If this is odd number, it will be half integer, okay? From now on, we call this quantum number J, and therefore we can rewrite all the answer in terms of J. The highest Z component is JH bar. The lowest is minus that. And using J minus, it will take this to here instead of H bar. Okay. And we also derived this. Okay. Thereby putting in JH bar for beta maximum, we have this very familiar form of the magnitude square. Okay, so let me summarize. This is the end result that I also give you at the beginning. Okay, let me emphasize one more time. The results here make use only of the 6 commutation relations of x, y, z, and j square component, and nothing else. Okay. Therefore, the answer will be general as long as you have found a new angular momentum, whatever it may be, that obey these 6 commutation relations. Then you can make use of all the answers here. The magnitude square must take on this very particular form, j times j plus 1 h bar square. Okay, actually more familiar should be the square root j times j plus 1 h bar. Okay, that is the magnitude of the angular momentum. Another very important result is that this quantum number j cannot be arbitrary. It can only fall into 2 classes, integer and half integer. Okay. Next, for a given j, that is to say, you know the maximum value of the z component, the z component can take on jh bar and minus 1 h bar, minus 2 h bar, and so on, all the way down to the minus jh bar. And all together, you count the number 2j plus 1 possible values. Okay, so that ends the proof. Okay, now, one final remark before we take a break. And this is important because we have seen orbital angular momentum for one special case, integer. J is integer. We have seen spin equals half being another special case of j being half. So this set will allow us, at least make us more comfortable later on when we see some angular momentum with the j quantum number being 5/2. Okay, that will happen if we have a d state and the electron with spin half. So you have a L equals 2, and then you have a S is half. How to add them? It's possible to get j equals 2.5. Okay, and from at that point, if you play with the logic, the total angular momentum is yet another angular momentum. Thereby, all this form follows. That's fine. Okay, it's not violating anything. Another important point in physics, but not here, we don't use it too much, is that it turns out that all the particles in the universe, they can be characterized by its spin angular momentum. And there are 2 classes. Either they take on integer spin, say spin 0, a spin 1, okay, or spin half, okay, half integer or integer. So again, at that point, you will not be frightened or scared off, okay? You know, that is what nature provides to all these particles, only 2 options. And it's so important that it turns out for particles with spin being integer, 0, 1, for example, they behave in one way called bosons. That has to do with your thermal and statistical physics course, okay? And for particles that takes on half integer spin half, for example, electrons, leptons, muons, or all those things, okay? They behave differently. They behave in a class of behavior called fermions, okay? So understanding that the commutation relations only allows us these two possibilities, I believe, is something that undergrads in physics should know. At least should know the final conclusion and the logic that comes from commutation only. The step in between may be slightly abstract and complicated, but the fact that from the 6 commutators, we have this box of conclusion, that is a piece of knowledge that students should know, okay? So for this, the mathematical proof ends. I will take a break and then we will make some sense out of it and then discuss how to add orbital angular momentum into spin angular momentum to get a new thing called total angular momentum. Okay, so that is the plan for the next hour. Okay, so have a short break, 5 minutes from we will resume.